Good afternoon. Welcome to the first session this afternoon. The first speaker is Uwe Fischer. He'll be talking about Trans-Planckian effects in analog gravity using Bose-Einstein condensates.
Dipolar Bose-Einstein condensates. Thank you very much for the invitation to beautiful Brazil. I'm from Seoul National University in Korea. I came here from Germany because from Korea it's quite a long way to travel. This is, by the way, our group logo, almost self-explanatory, I guess. So, not all of you know about analog gravity or the very concept of analog gravity. So let me give a lightning review on 2 slides of analog gravity. Analog gravity deals primarily with sonic spacetimes. Let's look at this picture here. Copyrighted Bill Unruh, who did first have this beautiful idea. Imagine you have some stream going down this rock here, a waterfall, and that's like a kind of high-tech waterfall. At some point, the speed of the flow exceeds.
Microphone behind you.
Well, people in this room will hear me anyway.
But not YouTube.
Yeah, not YouTube. Yeah. Okay, so imagine you have a high-tech waterfall, and at some point, the flow speed exceeds the speed of sound in that system. Imagine you also have in this world, you have fish which have ears but no eyes. So, suppose they also have voices. And that fish here can yell, and that fish can yell. The fish which is on the left, however, cannot be heard by the fish which is here upstream, before with the speed of sound. So here, that's these green lines here indicate the sound cones. You see the deformation of the sound cones here. They are dragged downwards by the increasing flow speeds above the speed of sound. That's the picture of dragging of the sound cones. It's very much like in curved space-time. So this guy cannot be heard. This guy here cannot be heard by this guy. That's the sonic horizon. And more formally, when you consider the velocity perturbations, so the little waves on top of the given backgrounds, some density and velocity distribution, these velocity perturbations, these equations can be shown, I will go in slightly more detail on the next slide, can be shown to satisfy the equation of motion of a minimally coupled scalar field in curved spacetime. It's just a one-to-one correspondence. Every wave equation, to remind you, is relativistically invariant. It replaces the speed of light by the speed of sound. That's very obvious. It's Lorentz invariant, provided you accept that the speed of light is replaced by the speed of sound. And this is here the metric element of that space-time. You see what enters the density and the velocity of the fluid. And here you can see G naught naught changes sign. That's the sonic horizon. Very much like in a black hole. So you have a perfect fluid. You can readily derive what I just said from looking at the equations of motion of that fluid. Very well known. Every undergraduate student should have seen this. It's the Euler equation here, amended by what is called the quantum pressure term, which exists in BCs, the things I will be talking about. I write it here for a local equation of state. We will be dealing with non-local equations of state because we deal with a dipolar system. And there's some external potential here, which, for example, might be a trap to keep the BC in place. That's the continuity. We will now expand velocity and density perturbations to linear order. We get an equation which is looking like this for the scalar potential, which is the velocity potential. So we have some inert background. Inert, I put that word because Gaio will be talking in the next talk about giving up inert in some sense. So this was originally coined by Bill Unruh. There is some early predecessor by Anthony Trautmann. in 81, this is a very good review for everyone here in the room who wants to learn the basics of analog gravity by Matt Visser. And very recently, 22nd of August, a couple of days ago, there was a Nature Reviews Physics where the possible consequences of this story for what you might call quantum gravity were discussed. I was a referee of that paper. That's also mentioned. So I know the paper. So we will consider, as I said already, a non-local equation of state. The usual systems, which are called BCs, which are interacting bosonic gases, at ultra-low temperatures, they interact by contact interaction potentials. Phi to the 4 theory for the field theorists. That's the most commonly studied paradigm. What I will, however, study is that the interaction is non-local and anisotropic. When you have a contact interaction, obviously it's local by its very definition, and it's also isotropic by its very definition. What I will study is a non-local and anisotropic Manivada system. Put the microphone on, else the noise level is too high. Like this is enough? Like this is enough? Like this is enough? But then this thing is a problem. So there's some difficult topology. I will not be talking about topology in this talk. A more tricky topology. Okay, so non-local and anisotropic systems. So not a contact interaction, but anisotropic, non-local interaction. That's a dipolar BC, which I will be discussing. So here we have a simple example of such a dipolar BC. It's not particularly comfortable. So a dipolar BC, we consider a pancake, and we consider dipoles oriented perpendicular to that pancake, for example, but we can also tilt it towards the plane of that pancake. This is this picture here. What you have when the dipoles are oriented perpendicular to the pancake is that the interaction energy is predominantly positive, because side by side means repulsion for dipoles according to the dipole-dipole interaction potential. When they're head to tail, obviously, like this, the dipole interaction energy becomes negative and the thing becomes highly unstable. So because the preferred configuration is, of course, that the system is doing this, collapsing. This is in between, when it's just a sphere, that it averages out to 0. So we can either consider a quasi 2D pancake, like depicted here, or like depicted here, a quasi 1D cigar. Both of these systems have in the meantime been realized. Actually, the quasi 2D pancake very recently. So what are these systems? Usually they are systems where the dipolar coupling is large enough, because the dipolar coupling depends on the square of the dipole coupling constant, of the dipole moment, sorry. The dipole coupling constant is the square, proportional to the square of the magnetic dipole or electric dipole moment. So what you have available atoms which have naturally a large magnetic moment are dysprosium, erbium, chromium. They all have been realized in the lab. One can, in addition, tune the contact interaction coupling, which is also always present, by Feshbach resonances, and then one can reach a dipole-dominated regime. So when the ratio of the two coupling constants is approaching infinity. These are the labs here. Electric dipoles, so heteronuclear molecules, are holding even greater promise, because when you consider the typical atomic or molecular rather dipole moment of 1 dBi, the coupling constant is 10 to the 4 times higher than for 1 Bohr magneton. These are some labs trying to do that. Molecules are just much harder to BC, to Bose condense, because they have internal degrees of freedom. They are much more nasty. They are heating much more easily. Okay, what I will be considering is Boglubo theory formally. That's the holy grail of all of physics for me. So this is a picture from an old paper of mine from 2006. Here you can see the essence of the spectrum, and a more recent paper here. Likewise, of course, the same kind of spectrum. This line here is the usual contact interaction spectrum. So when you adjust contact interactions in the BC, and when you turn on the dipolar coupling, what you get is a so-called Rotor minimum. It's a slight misnomer because it's slightly different than from helium-2, where it was originally introduced by Landau, but it is used in, in the community, let's say. That's why I put it in inverted commas here. So you can see the system here obviously becomes unstable when the Rotor minimum touches the k-axis. We will mostly be interested when the Rotor minimum is deep, but the system is not unstable. So the blue line here on the right. This quasi 2D has recently been realized, in fact. This is a Korean graduate of the Catalytic group, which I also know well. Okay, so what is Trans-Planckian here? Planckian is everything which is relativistically invariant. So this means this corner of the spectrum here. What you need is, you want to have sound waves which have omega equals Cs times k. As I told you already, the wave equation is relativistically invariant. It's Lorentz invariant. So up to here, up to this point roughly, you have Lorentz invariance of your system. Pseudo, of course, Lorentz invariance. C is replaced by Cs. Then, after that, Lorentz invariance is broken in a very specific manner. And namely in the manner, which will turn out to be very important, that there is almost no cost for excitations in the Trans-Planckian sector with Trans-Planckian momenta. Almost zero energy. That's crucial for our whole story here. Because this is where all the effects come from. Okay, so why is this important? Well, it constitutes, let's say, at the very basic level, a minimal length scale variant of phenomenological quantum gravity, so that you just cut off the Lorentz invariance somewhere here. You say Lorentz invariance is gone at some length scale, and something else sets in. Also, what I should mention is in the cosmological context, in the so-called Trans-Planckian problem, which I also worked on, in the Trans-Planckian problem in inflationary cosmology, this kind of spectra here, where the deep Rotor minimum, have been studied 20 years ago already, or Richard Brandenberger, for example. And then one might also ask, and that's exactly the question which we addressed, is whether the scale invariance of the cosmological power spectrum is maintained when you have violations of Lorentz symmetry in the Trans-Planckian sector. And what we have shown, I will come back to that it is not in our case. Next, the very fact that one can study in a controlled manner, in a microscopically controlled manner, deviations from Lorentz invariant quantum field theory predictions. So those in this room which know this book, when you take your Birrell-Davis and you study what it all predicts, these are Lorentz invariant quantum field theory predictions, are such deviations which come from the Trans-Planckian sector observable for low energy phenomena, for example, like the Hawking radiation. And the main motivation which underlies all the program here is for real gravity, we have no clue how to do that. Because we don't know what is the Trans-Planckian physics for real gravity at all. One basic problem which makes this mandatory, and that's why Hawking radiation is a beautiful microscope for all future physics, is one has an infinite blue shift, obviously, when one traces back because of the gravitational red or blue shift, depending which direction you talk about. If you look at some quanta at infinity and you trace them back all the way to the black hole horizon, they will experience an infinite blue shift, obviously, because of gravity. And this means that Hawking radiation delivers, potentially, at least clues for quantum gravity Trans-Planckian physics, which is where we expect quantum gravity to be relevant. And an important thing to note is that only certain classes of dispersion relations, that's what Bill Unruh and Ralph Schutzold found here in 2005, only certain classes of dispersion relations yield Hawking radiation modifications. And in the very final paragraph of their conclusion, they say, if, and I noticed this afterwards, if the spectrum bends down in the Trans-Planckian regime as a deep minimum, one will see modifications. That's our story. Okay, the simplest case which we can study is, before going to the interface problem, so the horizon problem, is that we consider, that's a well-known formula here, for everyone who in this room who has seen Bogolubov theory, and every physicist should have seen it. That should be a well-known formula. This is just a constant here for contact interactions. That's the Fourier transform of the interaction. This is just G, small g, for contact interactions. That's the well-known Bogolubov spectrum in condensed matter, or in quantum optics, or anywhere in this world. The thing is that now we go a bit more far, because with long-range anisotropic interactions, as I will argue, we can get genuine quantum many-body physics, not just the relatively trivial one of the contact interactions. Well, it's a strong word to say relatively trivial, but it's way more complex, as you might imagine. I will have these three topics here. Very briefly, an old paper 6 years ago, the breaking, I just referred to that, of the cosmological scale invariance by the Rotor minimum. That's this paper here. Then the continuous variable entanglement and steering of quasi-particles by quenches. I mean, this is a conference in honor of Viktor Dodonov, so that there must be a part related to the dynamical Casimir effect. That's the second thing here. And we will see that in regard to that the quantum mechanical non-locality is strongly enhanced by the anisotropy of the interactions, not the long-range nature, not that trivial thing. It's the anisotropy of the interactions. So this is one slide on this breaking of cosmological scale invariance. What you see here in this picture is a simulation of the density, but that's the same, but the conjugate phase fluctuations in the BC. So this is the correlator in the quasi-particle vacuum of the phase correlations of the system, this thing here. I just do a Fourier transform. This is the volume of the system. And what scale invariance for large cosmological times means is that you have that the power spectrum has this form here. Note that this is a quasi 2D system for stability, which I consider here. The usual formula would be here k to the minus 3 in the real cosmos. So this is the quasi 2D plane, which you see here. And this is a depiction of a simulation in the real space of this guy here, this correlator, this phase fluctuations correlator. And the scale invariance means that when you zoom in, so this is the scale invariant picture when you have no rotor minimum. This scale invariance means you zoom in to smaller and smaller and smaller and smaller scale, it always looks the same. It's a fractal structure. That's scale invariance. And this scale invariance is broken by the rotor minimum. The deeper you make the rotor minimum, the more the scale invariance is broken. Certain structures appear. The scale invariance is lost. The rotor minimum breaks the analog cosmological scale invariance. That was very brief on this old paper. Now we come to the entanglement and steering part during a quench, the creation of quasi-particle pairs from the vacuum. And I will argue that these quasi-particle pairs created from the vacuum are entangled or even steered. So one slide to remind you what is entanglement and steering. For many people, if it would be a quantum information audience, I would skip that slide. But this is not a quantum information audience. So in his Annus Mirabilis 1935, Schrödinger coined two notions. One of these notions is entanglement, the non-separability of quantum states. And the next thing is even more mysterious, steerable states. That if you have a bipartite quantum system, that one of the parties can actually steer what the other party will measure. Usually, of course, it's Alice, which is steering Bob, like you in the usual relations with man and woman. So, what you can say very roughly to give you an idea is that bipartite steerable states have half of the Bell non-locality. The most strong non-locality you have in quantum mechanics is Bell states, where both parties can, so to speak, steer each other in a sense. For the steerable states, just Alice performs measurements, uncharacterized, so to speak, measurements hidden to Bob. So Bob doesn't know what Alice, what her pointer is pointing to, what she's measuring. By that measurement, however, she determines what Bob will measure. So this has to do with inferred standard deviations. One can write that formally. Very roughly, again, to summarize, steerable quantum states are a subset of entangled states. They need more strong conditions that I will show you, and a superset of Bell states. So how does this work for continuous variable systems? Most people are familiar with entanglement and steering for qubit or qubit systems, but how does it work for continuous variable systems? So let's go back to Bogolubov. That's the density fluctuation operator in Bogolubov theory of any quantum gas or any system, which can be described by Bogolubov theory. This is the quasi-particle field operators, these phi guys here. And that's UK, UVK is just the standard Bogolubov amplitudes. Then we can write the density correlation in Fourier space. It looks like this. It has two components in it. One of them is the mean quasi-particle occupation number. That's this guy here, as usual. And the quasi-particle pair amplitude is the next thing. These are the standard things which appear, for example, in the BCS theory also, obviously, but it's also a Bogolubov theory. So this is the density correlation in Fourier space. Now, how can we quantify and tell whether entanglement and steering are present? This was set down by this gentleman here. I want to honor in particular Renaud Parentani here, because, for many reasons. But we can use the density correlations I just referred to as an experimentally accessible measure of quasi-particle entanglement. And I stress here, experimentally accessible measure, because it's a measure which has to do with commuting observables, with densities. So one thing is the entanglement, non-separability of quantum states. This you get, as you can show, is when at some given point of time, the correlation function, density correlation functions, is below the vacuum value. The vacuum value is this guy here. And when it's half of what the vacuum value is, this is obviously a more strict criterion, more stringent, then it's a steerable quantum state of quasi-particle pairs. Obviously, we have quasi-particle pairs here, k minus k. They're created in pairs, because we conserve momentum, of course, during the quench which we perform on the system. We do a quench, as I just said, so we compress the gas very rapidly, or if you like, we change the boundary conditions very rapidly. That's the dynamical Casimir effect part here. We make the wrap much more tight very quickly. Of course, you can also do it in an analogy to cosmology. Then you have cosmological particle production, but cosmological particle production is nothing but dynamical Casimir effect. That's the very same thing. The quantum optics guys call it parametric down conversion, but it's all the same math. So we compress the system very rapidly with some different speeds here, collapsing universe if you like. And then we can compute our density-density correlations. We can normalize it by the vacuum value here. So you can see here when we normalize the density-density correlations by the vacuum value, when the ratio of this to this is below 1, it's entangled, and when it's below 1/2, it's steered. So you can see this graph here. That's as a function of time, the density-density correlations. And you can see it's rather easily entangled. But if the rotor minimum is deep, like here for this purple curve, this is the excitation spectrum. That's our rotor here. If we have a deep enough rotor minimum, either the green or the purple curve, we get steered pairs of quasi-particle excitations in our quenched quantum gas. Well, that's why we get manifestly steering. And again, I emphasize it, the potential, of course, increases for steering. One should write here maybe steering potential, but also entanglement potential increases. The reason is that the interaction are anisotropic. Sometimes they are repulsive, sometimes they are attractive. The quantum mechanical non-locality, because steering is nothing but a manifestation, a formal way to express quantum mechanical non-locality, increases, and the anisotropy of the interaction increases. Because the rotor minimum comes exactly from the fact that the interaction can be attractive. That's the very same reason, the very reason for the rotor minimum. This was published here. Okay, so now we come to a much more integrated story. We come to interfaces and horizons, or the particle horizons in a dipolar BC. When we have a special homogeneity, when we have, let's say, go over from one coupling constant to another coupling constant, or when we go between regions of different spatial density, obviously we get a scattering problem. We solved, Caio solved it mostly, together with his wife Luana to some extent. She also contributed as a mathematician, because what we discovered in that paper is that the interface here is a sound speed jump. We discovered that we got a novel hypersingular integral equation, which needs to be solved to solve the scattering problem. It's singular only at isolated points, which is novel, apparently, as far as we found. We demonstrated a strong impact of the rotor minimum. For some parameters, the barrier can become opaque for certain frequencies. This is published here in this Signpost Physics. I will not discuss this in detail because it's very mathematical. Okay, now the main part of our story. The black holes, or the dump holes. Bill Unruh called them dump holes for obvious reasons. He said they're not black, they are dump. Of course, the PhysRef editors didn't like that title. So they renamed it Sonic Black Hole, because if you just call it dump hole, it might sound a bit offensive in cases. Okay, so what is the main reason for all our program here? First of all, if you want to observe Hawking radiation for solar mass black holes, it's just an absurd undertaking. Completely absurd. Because what you would have to observe is, for an astrophysical, for solar mass black hole, you would have to observe a 60 nanokelvin temperature on top of a thermal spectrum, another thermal spectrum at almost 3 Kelvin. That's obviously, well, to put it very polite, a formidable undertaking. That's one of the very, I mean, this is why Bill Unruh wrote his paper originally. The original title of the 81 paper was Experimental Black Hole Evaporation, question mark. So, and we got in the lab now, well, most people agree in 2019 this was done. There was somewhat not quite accepted experiments before that. But in 2019, the first unambiguous observation of Hawking radiation was performed by the Steinauer lab in the Technion in Israel. And this is a major milestone for all of physics. I don't exaggerate here. That Hawking radiation actually exists. Note here that you're not led astray that for Hawking radiation, no Einstein equations are necessary. What you need is a space-time horizon and excitations, quantum field excitations, which propagate on the top of that space-time background, which satisfy Lorentz invariance. So, this is a picture here how the experiment was done. Steiner was swept at a rapid speed, I mean exceeding speed of sound, a Bluetooth tuned laser through the BC. This is the outside of the black hole here. That's the horizon, and that's the inside. That's a real picture from the paper. This 2019 paper. Okay, now dipolar black hole radiation, Hawking radiation. When we have a rotor minimum, and I will show that on the next slide, the spectrum is expanding vastly in complexity. The number of possible ingoing and outgoing modes, to make it clear here what means ingoing and outgoing is going towards the horizon and outgoing is going away from the horizon. The number of possible ingoing and outgoing modes just tremendously increases because the rotor minimum. We will see that on the next slide. So you can see this by the group velocity just. Of course, the sign of the group velocity tells you if it's ingoing or outgoing. And if you know what the horizon is, of course. You should also know that. So one can get highly non-trivial density-density correlations across the horizon. And these density-density correlations, well, just for the entanglement and steering, they constitute a signature of the Hawking radiation. This was found essentially first 15 years ago. And they mean the entanglement, or one can map them, let's say, to the entanglement of the Hawking pairs. Because also in Hawking radiation, you have pairs of quasi-particles which are created, like in the dynamical Casimir effect, or in cosmological particle production. The black hole model we used is the following. It's a nice colored picture here, so not an experimental one, it's from our theory paper. We consider a jump in the Mach number. The Mach number defined as usual, the ratio of the flow speed by the sound speed. And this corresponds to a density jump at x equals 0, so it is vertical dotted line here. Here's the upstream flow. The d is the direction of the dipole moment of the particle in this quasi 1D configuration, and theta is some angle here relative to the axis. The contact interaction model, a similar one, was studied by Galitsky and co-authors here in 2019. So now, as I said, we consider a quasi 1D cigar. So in these transverse directions, the system is very strongly compressed, very strongly trapped, and essentially the flow is 1D. The depth of the rotor minimum, which we discussed now many times already, here means a quasi 1D-ness. One can define a parameter like that. The quasi 1D-ness corresponds to the depth of the rotor minimum, because when you release the transverse trapping and make the cigar thicker, you will have the tendency to make the system more unstable. Okay, so there's a parameter beta here. The L perp is just the harmonic oscillator length in the perpendicular direction of the trapping. How many minutes? Huh? No, but I began, I think, at 15, right? I began at 15, if I remember correctly. So the transverse trapping length over the coherence length. Coherence length, for those which are not familiar with that, is just the length over which the order parameter of the system varies. So the density of the system varies. It's defined by the coupling constants and the density of the system. We have the following parameter regimes. We have a completely deep quasi 1D system, which is completely stable. So basically no rotor minimum. You can see it depends on this parameter here. The more thick we make the cigar, the more rotor minimum we get the rotor information. Then we make it more thick because we suppress by compressing the cigar the instability. And when we make more and more thick, we get to a regime where a so-called, and that will be shown to be crucial, Hawking rotor branch emerges, a new branch of excitations emerges, which is contributing to the fact, crucially contributing to the fact that the Hawking radiation is completely different in that system, or has a very large gray body factor, which is not black body anymore. And then the system finally becomes unstable. Here's the spectrum of the system. And what I only show here for simplicity with these blue dots here is only those modes which are going away from, which are going towards the horizon, ingoing modes. The outgoing guys are not shown here, only ingoing guys. And this one here is what emerges. So these various modes here emerge. And there's one, sorry, when I refer to this here, to this Hawking rotor, there's one mode which you see comes from upstream, so from outside the horizon, is propagating towards the horizon, and I call it KR. That is this rotor branch, this new Hawking rotor branch I'm referring to. This pH here, which is inside the horizon, and which is going towards the horizon, it's scattered there, is the usual Hawking mode for the responsible for the Hawking radiation. The other guys we don't care about in a moment. This is just one configuration I'll show here. So you see that's the flow speed is always constant, and there's a density jump, which means a jump in the Mach number, which creates the horizon. Very simple configuration, but we could solve it. That's why we chose it. Okay, now what is the energy balance in the system? Because the energy balance, of course, decides what is the flux actually of particles which you get in infinity. Here, that's the norm of the incoming scattering channels with respect to the Bogoliubov scalar product. You must define a scalar product for the modes, of course, and that's exactly that scalar product. Sigma 3 is the usual Pauli matrix, the third one. And the crucial thing is here that the sign of this quantity appears here. This is the group velocity, this is the density. If you have positive norms, so if this guy here is positive, then you get a set of excitations which have positive energy. And if this guy is negative, so the norm, the quasi-particle norm in the Bogoliubov space corresponds directly to positive and negative energy. That's a one-to-one correspondence. The positive energy set has positive norm, and a negative norm, so if this guy is negative, is a negative energy set. And if we now look at the energy balance after we normal order the quasi-particle Hamiltonian, we get one part which has positive energy, as you can obviously see here, positive sign, and one part here which has negative sign. And those guys here, these guys, they are the Hawking radiation. They reduce the energy of the system. They carry away energy. And the difference which we have here is that this set here, in distinction to the contact interaction, now has two members instead of just one member. That's the difference of our story. This is the black hole radiation, this guy here. And the Hawking flux, we consider, of course, spontaneous Hawking radiation, so at temperatures T equals 0, and not simulated Hawking radiation, which you can also consider, but we consider the real Hawking thing, the spontaneous decay of the black hole, dump hole here. We can consider this power spectrum to quantify this. That's the power spectrum here. This is the scattering coefficients for certain channels K here. Again, this sign appears. The group velocity appears here, and just this difference compared to this here without the group velocity. This is just the power spectrum of the Hawking, of the flux. The total radiation power to the outside of the black hole, which is at minus infinity, so somewhere here, downtown or something, is this thing here. If we integrate the power spectrum as usual of all frequencies, we get the total flux, total radiated power. We have just global conservation here. This is also a side remark. When we have dipolar interactions, because they are long range and anisotropic, but mostly because they are long range, we have no local energy conservation. This is why non-local field theory is much, much, much harder. One primary reason why non-local field theory is much, much harder than local field theory, like 5 to the 4. There's no local energy conservation. In the dipolar case, that's why I put it in red here, we have two branches. So two branches, these two guys here. This alpha is the index of the modes. Two branches which contribute to the Hawking radiation. One of them is this rotonic branch, and the other is the usual Hawking branch. So this is the usual Hawking branch. That's the rotonic branch, which only appears if there's a rotor minimum present. So now, what is the TransPlanckian? So rotor minimum modification here of the Hawking radiation. It's Planckian in Lorentz invariant theories and also for contact interactions, by the way. But it has a large gray body factor when we have a deep minimum in the spectrum in the TransPlanckian sector. We can define, that's the usual, and I put the sign correct here, Victor, minus, because we have bosons. So what you have is, you can use this as a signature, of course, here. Then when you compute omega times n omega, it should go to the temperature when it's purely thermal at omega goes to 0. That obviously follows from this. So we can define some effective black hole temperature. If you make the product of omega times f omega, we can make this. Yeah. Kaya, should I not read n omega here? Does it read f omega? F omega is correct. Okay, it's correct, yeah. But I copied it from our paper, so. Okay, so one can define an effective temperature by multiplying the power spectrum with omega. And omega goes to 0, if it's effective temperature. And then we can define a gray body factor as a corollary. What we have is when this guy is exactly 1, we have black body by definition. And when it's not 1, we don't have black body. So how does it look like? This is a lot of plots, so let me explain. This is the depth of our rotor minimum here. I remind you, beta is 0. It's essentially no rotor minimum. And the depth of the rotor minimum gets higher and higher if you increase the beta, this quasi 1D parameter. Here we vary the downstream Mach number, so the Mach number inside the black hole. And what you can see here is that there is this peak in the temperature at this beta here. So when the Hawking, this KR branch emerges, you get a peak in the temperature here at this point, always, as you can see. Another thing which you can see is that, well, when you look here, is the gray body factor. I remind you again, the gray body factor for black body, of course, should be 1 exactly. You can see the deeper the rotor minimum, the more we go towards this green guy, the more gray body it gets. It's not black body at all anymore. To no reasonable approximation, it's black body anymore. And down here, I plot how the frequency and the power spectrum are connected. And you can see a correlation with the upper part here. Here, this is the spectrum. We published this. This is omega as a function of k. You can see the rotor minimum here. So this is published this year in June. And also, what one can say, that's another thing which I should observe, is that one can see that, if one looks more closely, that if one compares that the dipolar black holes are effectively hotter than the contact interaction black holes. If one makes a, if you like, fair comparison. If you look at the temperatures you can get for the same configurations. And yeah. Okay, so conclusion. If you have non-local and anisotropic interactions, like in the dipolar BC, then study the black hole, the black holes, for example, but generally the analog gravity in these systems, we have a profound impact on quantum field theory predictions in curved spacetime. And again, this is essentially not studied by the vast majority, basically all of field theorists, just because it's much harder, non-local and anisotropic interactions, than when you just have your usual Young-Mills business. The standard model is only contact interactions. There is no other interactions. But this is, in our opinion, a truncation of the actual physics. Everybody knows, already from the undergraduate lecture, there's a multipole expansion, right? You cannot just say you only take monopole interactions. That's just not physical. You neglect all details. You only study very long range physics. Okay, it's a novel arena for the study of Trans-Planckian effects. I discussed that at length. And we discussed here, or we constructed, the first analog gravity simulation of a dipolar black hole. And we have shown that the Hawking radiation spectrum, so that's a clue to quantum gravity, that microscopic quantum gravity is deeply affected. Now, what does it possibly mean for the black hole information paradox? Is there an impact of the rotor minimum? Hawking radiation is known to be deeply connected to the black hole information paradox. Because when some star collapses, which is above the critical mass, all informations about initial states go down the drain. What remains is a black hole which is as bald as me, at least which has here no hair, at least classically. So all the information somehow is lost. There's only 3 parameters remaining, maximally. Because the interest here is, of course, in the lab, when we neglect 3-body losses and so on, we have approximately unitary evolution of the system. So we can prepare the system with some exact, well-specified initial conditions and study the many-body problem. Unitary evolution. In a unitary system, there is no information paradox. And when there's a final quantum gravity, there is no information paradox, as long as it is a unitary theory. Information paradox is gone with the unitary theory, because there is no information paradox by definition. So that's a possible arena. And finally, that's also what we are doing now, is in this dipolar black hole, as I argued, we have a rather big increase of the possible scattering channels and quasi particle modes. We can have here, we can, for example, study bi or multipartite entanglement and even steering. And I recall that the dipolar anisotropy enhances the entanglement potential. There's a lot to be done for quantum many-body physics in dipolar systems, not only analog gravity, but analog gravity is just what I find most fun and to work with, and which is just most interesting by far, because it connects various subdisciplines of physics. Okay, so nowadays you have to pay if you don't want to have ads in some apps. You didn't pay, so there's an ad at the end. Thank you for your attention.